In this video, I would like to show you how an old airplane gyroscope shows the rotation of the Earth. This is a vintage air-powered, purely mechanical heading indicator gyroscope, also known as a gyro compass, but I'm going to try to call it a heading indicator gyroscope. I've got it set up so it's pointing at the North Star so that it will measure the full rotational rate of the Earth. And as you can see, I'm starting at about 11 o'clock, 11:01:40, and it's pointing towards the south. Here's the east, and let's play. It's playing at 60 times speed, so each minute only takes a second to watch, each hour only takes a minute to watch, and this is going to go for about an hour, so it'll only take you about a minute. So there's 15 degrees in an hour, and 60 minutes in an hour, so a third of an hour is 20 minutes and 5 degrees. So this is the 20-minute mark, the 40-minute mark, and the 60-minute mark. So I'll let it play. And as you know, the sun rises in the east, goes up and sets in the west, and like this is tracking the sun, you can see it's coming up in the east, going over and setting in the west. This should be our 40-minute mark here. I'll pause it again when we get there. Okay, right on the money. Let's keep playing. This is the 15-degree mark. This is 0 degrees, 5, 10, 15. And 1 hour should take us right here to the 15, but it's an old, worn-out gyroscope, and so it has a little bit of its own drift, which is offsetting this, but still it's very close. So you can see 12:01:40, whatever. It almost got us to the 15-degree mark. I'm going to play it and see what it takes to get it to the 15-degree mark. So yeah, it took an extra 5 minutes to get to the 15-degree mark. But still, that's very close for an old gyroscope. So it's definitely showing the rotation of the Earth to be about 15 degrees an hour. And if you would like to see how I set this up and how I did tests with a total of 3 gyroscopes, multiple tests, and they all confirm the same thing, go ahead and watch the video. But if that's too lengthy for you, now you've at least seen the Earth's rotation with a purely mechanical, air-driven gyroscope. Gyroscopes I used, they're all heading indicator gyroscopes. This one is the most worn out one. It gave some useful results and some erratic results, but you can see it's got the wheel on there. This one's also been modified. I took the back off and then made this vacuum cover with plastic so I could quickly open it up with it running and fiddle with it. The next ones are just unmodified. It's going to be embarrassing if I break my glass plate. See, they're just Sperry gyroscopes. You put the vacuum in one of these little ports, and there's a filter right there to keep dust from getting in there. And then this one's another one similar. So those are the 3 gyroscopes I used for my test. Okay, I've got the back taken off this gyroscope here. This is a heading indicator gyroscope. So once it's spin up, you can set your heading and you pull this out and then it'll track. But right now it's not spinning, so inside you can see we've got the brass flywheel that spins pretty free, and then this can tip, and then this can rotate to indicate your heading. Here's a little balancing nut that allows you to balance it to reduce its sensitivity towards accelerational force. And then over here on the other side, this is your latitude nut right there. That can induce, you can move that in or out, and you can induce a drift clockwise or counterclockwise on the, east or west on the, whatever you want to call it, the scale here. So let's go ahead and spin this thing up. See, there it goes. Now you can see it force I put on here translates directly to right angles on that wheel. And if I put a force, it's going to be hard to put just, but if I put a force on there, see, it moves the whole thing. So you can see imbalance on this here nut would cause a drift to rotate that way, whereas imbalance on this would simply be translated to that axis. You see, now you can see it's holding rigid in space. So if we were to turn this back over, synchronize it, see, now it's definitely tracking. Gyroscope spin up, and I want to show you the degrees of motion that it's sensitive to. As you can see that if I rotate this way, it stays stationary in space. If I go this way, nothing stays stationary in space. If I go this way, it stays stationary in space. So you can see the brass wheel stays on a plane there. See, I can move it up and then it stays there, or I can move it down and it stays there. But the one axis that doesn't do anything is the one that pivots around the axle of the gyroscope wheel. See, if I were to turn like this, I'm turning around. It turns, or if I were to bend down or bend up, that all tracks, but the one rotation that it doesn't track is this way, see? And so I'm using that to point to align the one insensitive axis to the Earth's rotation to get a baseline for the gyro's drift without Earth rotation induced drift. So if the Earth is rotating this way, I get a baseline that way, and then I turn about 180 degrees around so that then the Earth's rotation is at this axis, and it would then track the rotation that way. Alright, I am down in my basement, and I'm showing you my leveling table here. It's a sheet of glass supported in 3 points. Right here it's supported by this bolt stuck in a hole on this vibration dampener. It's a big cast iron and steel piece of a car motor, but it's pretty sturdy and stout. And the other 2 points are on these 2 adjusters. See, there's a point right there and a point right there. And so this glass is relatively flat and supported on these 3 points, so it doesn't rock at all. These adjusters are a triple stage adjuster. I have a real coarse adjustment here, then I've got a finer adjustment here, and then I've got a super fine adjustment here that actually moves in an increment of 1/millionth of an inch. So I can raise and lower each of these 2 points up or down by 9 millionths of an inch, actually. The increment here is a 9 millionths of an inch. So, I don't know if you can see that, but it's, yeah, there it is. Division is equal to 0.000009 inches. So this allows me to precisely level this. To level it, I got a high accuracy long, let me look at the length of this bubble level, long bubble level off of eBay. And so I align it this way to level it this way. You can see it's level. I take and I turn it at right angles. And it's pretty much level in that axis too. That's a super sensitive level. And just so you know the level's level, I'll turn it around. Put it there. Oops, didn't quite get it right. So you can see it's pretty level. That's a very sensitive level. Alright, the second part of my gyroscope testing setup here, on top of my leveled glass, I've made this adjustable angle board system where I can mount the gyroscope here, and I have a little camera up on a wire so I can point the camera at it and take a time-lapse video of the gyroscope turning. On the underside of this, I have 3 little leather pads glued on so it sits on 3 points so it can sit nice and steady on this glass without rocking or wobbling. It's real stable because it's sitting on 3 points, and since they're little leather pads I can rotate this around when it's time to change angles. Now let's see, I got a compass here. You can see with the compass that, can you see? There you go. That's about north, that way. So, since I'm at 48 degrees latitude, that means the North Star is about that direction. So I've got this kind of pointed generally at the North Star so that I can turn the compass so its sensitive axis is either towards the North Star so it won't detect the Earth's rotation, or at right angles to the North Star so it does detect the Earth's rotation. That way I can just swivel the whole thing around, but it still stays the exact same level because it's on a level glass, but it doesn't but it changes the orientation to the Earth's rotation. And then I have a little inclinometer here I put on the side, but I also have a little digital one. Can you see it? Yeah, see? So 42 degrees is about the difference between 90 and 48 degrees. So that's what that's all about. So then I just need to mount my gyroscope here. I've got a vacuum pump here which produces vacuum to run the gyroscope. So for my tests, I had the gyroscope mounted on the tilted angle board, and I had the little webcam up here to taking the time lapse looking down at the gyroscope, which I'm going to power up now. Okay, so I want to show you here how I had the gyroscope screwed down to the angle tilt board, and I just got it spun up here, and then I took the vacuum hose off. So my basic test procedure, since north is about that away, I point it, and the North Star for me is pointing right up that way. I would point the axis of this, I'd point the axis of this flywheel at the North Star, and then track the drift with the webcam, the time-lapse camera. The idea being that if the Earth was rotating around it this way, it would not be sensitive to it because it doesn't track the rotation that's on axis with the weight. So after getting a baseline, I would then, for the inherent drift in the gyro, I would then turn this around on the same flat surface here, and then realign this using the knob, which I can't do with one hand, but anyway, I would realign this to point straight up this way, and now, since north is this way, the axle and the flywheel is at right angles to the North Star, so then the Earth's rotation would then be added or subtracted from the existing drift of the gyroscope. So then I would compare the drift rate when the axle was at right angles to the North Star, and then compare that to the drift rate when the axle was lined up to the North Star. So that was the basic method. I did it with 3 different gyroscopes, this one and then the other 2. so that's how the vacuum pump runs this. And for my tests, I had the vacuum pump running continuously, and I had them connected up so that they were reached a state of equilibrium and they were running at a constant speed. But I'm not bothering to do that for this because I'm just showing you how this works. So basically, I would run it up with the 0 pointed at the North Star, you know, and I would take and set them up, cage them and turn them, and then pop that out, and then record the drift on the webcam. And then after getting a baseline for the gyro's inherent drift, I would then lock this and rotate this whole thing around. I would leave the hose on, but I'm trying to do this with one hand, and so you can see by rotating it around, I'm keeping it on the same flat leveled surface, so we don't have to suspect that it's changing level and that was changing drift. I wanted the drift to have only one changing influence, and that was the Earth's rotation. Then I would, after rotating it, I would zero it out and pop that out, and then still under air power continue to track drift, and then by subtracting, because now the North Star is that way, so now you can see now it is sensitive to Earth's rotation that way. So by comparing the two drifts, I could see what the difference in the two drifts was. Alright, so this is the first gyroscope I tested. This one ran for 1 hour pointing north, 1 hour pointing south, 1 hour pointing north, 2 hours pointing south, and 2 hours pointing north. So this is 8 a.m. to 9 a.m., 9 a.m. to 10 a.m., 10 to 11, 11 to 1 p.m., and 1 p.m. to 3 p.m. So it starts out at, we're right here in this first stage. It's pointing north, which should be insensitive to the Earth's rotation, because here's the wheel, the brass wheel of the gyroscope right in here behind there, and the axle's pointing straight at the camera almost, and straight at the North Star. And so you can see the compass is pointing about north. The needle's off because that's about my declination, and it's just a compass there to show you generally which way it's pointing. And so this time lapse is playing at 1 hour per minute. So in the timestamp, this is the hours, this is the time, it was 7 a.m. This is the minutes, 59 minutes, and this is the seconds, 23 seconds. But when I play it back, it's going to play really fast because I'm playing 60 times real time. So each minute will take 1 second, and each hour will take 1 minute. So this gyroscope was running for 6 hours total, non-stop, and the camera was running for the same period of time. And so I'm going to show you what happened. This is an old, worn-out gyroscope. Sometimes it's kind of erratic, sometimes it works. And for the first 2 hours, it wasn't very settled down. It was kind of acting erratic, sometimes moving one way, sometimes drifting the other way, sometimes sticking. But then for the last 5 hours, it was working pretty well. Alright, so I am going to start this. Oh, so yeah, okay, so in this position, it should not, according to the globe model, it should not be moving, but you can see it's going to be drifting here. So it immediately drifts. That's 5 degrees. This is 10 degrees. And this would be 15 degrees, but now look, it stops and changes directions a little bit, kind of wanders back and forth, and then it starts going again. So that's just, it's got a lot of loose parts in it, it's well worn out. See, now it's half an hour in, but it's already drifted almost 20 degrees. And then it stops and goes back a little, and our first hour is about up. But see, then it kind of stops there, it just sticks there. So whatever imbalance forces were causing it to drift kind of things shift around, and at the new angle it was just about balanced, and so it stop drifting. Okay, so that completes this part of our test. This was to show what happens when it's pointing north at the North Star. And now you'll see it quickly rotate. And so here we are rotated. Now north is here, so now it's pointing south, see? Before south was up here and north was out here. Now it's rotated 180 degrees. Now it's pointing south, and it should be sensitive to the Earth's rotation. You'll notice before this mark was counting this way, it was counting up. Now that it's rotated the other way, let's see what happens. Now we're in this here 9 a.m. to 10 p.m. 9 a.m. to 10 a.m. pointing south for 1 hour. So now you'll notice it's moving the other way. And this is very interesting because it's still on the same level surface as it was. Turning it should not have affected it. And you'll notice that right at 20 minutes we've gone almost 5 degrees, which is very interesting. And I stopped the playback, but the real camera for the 6 hours that it was running ran continuously nonstop. And I'm showing you every frame, but I pause it sometimes to stop and talk. So each one of these divisions is 5 degrees. So this is 5, 10, that's what that one is for, 15, 20, 25, 30. So likewise, this is 5 degrees. So it actually went 5 degrees in 20 minutes, or almost 5 degrees in 20 minutes, which is very interesting because the Earth is said to turn at about 15 degrees per hour, and this would be 15 degrees, and so this would be 1 hour's worth, and 20 minutes is a third of an hour, and this is a third of 15, so it actually tracked at exactly the Earth's alleged rotation rate. But that's where it got stuck in this particular run, because it hit a flat spot on a bearing or reached some equilibrium, and see, it stopped drifting. It's because it's old, worn out. Whatever the cause of the drift is, it can get in a position where it ignores it. So you can see the rest of the hour plays out and it just sits right there. You can see this is in the basement here. It's ugly, but it was on concrete and it was stable. Okay, our hour is about up. Okay, so this brings to the end the 9 to 10, and you'll see it rotate again. And now you can see it's back pointing north again, so now we're right here, 10 to 11 a.m., pointing north for 1 hour. I've reset it back to 0, and at this point it starts behaving relatively steady. So it's pointing north at the North Star, so it should not drift much in this orientation. You can see it's drifting a little bit, but here we are 15 minutes in. There's 15 minutes. It's drifted about a degree or so. 20 minutes. Half an hour, and it's still only drifted hardly more than a degree. Right now we're at 10:42, so we're in the 10 to 11 time period. And our hour is about up. There. So this is how much it drifted this time in 1 hour. This was the 10 to 11, pointing north for 1 hour. And I actually am going to save a screenshot of this because I'm going to compare it to later. So you can see I've got a screenshot saved right here that just shows this here at 11:00, which is like there. See? So I've got a screenshot that I already captured in advance because I'm going to compare it when we rotate this, and so I'll show you. Alright, so we've just completed 1 hour at north, and we've got about a degree of drift. If this is 5 degrees, that's about probably a degree roughly. We're pointing north, and now we're going to rotate the whole thing around on its flat surface So now it's pointing south. See, the red north needle is this way now. So now it's pointing south. Now it should be tracking the Earth's rotation. Right, see, it's 11 o'clock. So now we're here at this 11 to 1 p.m., 11 a.m. to 1 p.m. section pointing south. And let's see what happens. Again, this is playing 60x, so these are frames, these are seconds, these are minutes. And this is very interesting. It moved 5 degrees in 18 minutes. And again, the Earth's alleged rotation is 15 degrees an hour roughly, which is 20 minutes per 5 degrees. So you can see it rotated very, very close to the expected value for the Earth's rotation. But let's continue. You can see it slows down and speeds up a little bit, but that's just probably what an old gyroscope does. So we're reaching almost 10 degrees. And we passed about the 7 degree mark, 7.5 degree, right at about 11:30. And right now we're on the 11 to 1 p.m., the 2-hour period here. And I'm going to pause it right about there, 12:01. And look at this. It has moved. This is 5 degrees, 10 degrees, and this one would be 15 degrees. It moved almost 15 degrees in an hour. Now I'm going to bring this up and to compare it to how we started out. So see, this was at 11 o'clock, this is at 12:01, and you'll notice at this point, see, we were pointing north. See, the red needle's pointing down to north here, and here it's pointing up, so we're pointing south on this one. But back during the null mode, when we were pointing it north and should not have had any rotation, the gyro actually drifted in the increasing direction by about a degree. But you'll notice over here we've drifted about a degree short of the expected 15 degrees an hour. So what I'm going to do is I'm going to take and copy this little area into this picture over here, like that, so you can see how these two marks line up, and you can see that these are both to the left of their mark there by about the same. There's actually, if we compensate for the gyro's tendency to drift in the increasing count direction of about 1 degree per hour, we get very close to 15 degrees per hour when we're testing in the orientation that's sensitive to the Earth's rotation. So this gyroscope really did measure very close to 15 degrees per hour over a 1-hour period. But I let it run for another hour, and it actually started to speed up a bit, probably because with the 0 straight up it was balanced reasonably well, but as it tipped, then things shifted and the weight shifted because the bearings aren't perfectly adjusted, and then it sped up. But not astronomically. You can see here's was our 1-hour mark roughly, and so here would be our 2-hour mark, but it's going to reach our 2-hour mark before 2 hours is up. But hey, this is research, and I'm showing you what happened. So yeah, see, 15 minutes before our 2-hour mark, we shot right past our 2-hour mark. And I think it goes like probably out to here, like 10 degrees past in the 2 hours. Okay, so that was our 11 to 1 p.m., or 11 a.m. to 1 p.m. And now we're going to rotate it back around and do 2 hours pointing north from 1 p.m. to 3 p.m. just to show that the gyroscope does drift less when it's pointing north than when it's pointing south. And see, again, now it's kind of just wandering back and forth, because see, now we're pointing north instead of south. And so it started to drift one way, and now it drifted the other way, and I think it ends up right over about here after 2 hours. So in the non-sensitive orientation, that is to say the orientation that's not sensitive to the Earth's rotation, it drifted less than 5 degrees in 2 hours. But in the orientation that it was sensitive to the Earth's rotation, it drifted about 15 degrees for the first hour, and then some more for the second hour. So there's 2 o'clock. See, it comes over. Now it's starting to go back a little bit, it looks like. Makes it almost back to 0. And then it starts heading back to where it was. And there we are. That was that was a full time-lapse, an unedited, uninterrupted time-lapse video for 6 hours straight. The vacuum pump was running for the entire time, the gyroscope was running for the entire time, and there was nothing cut out in the recording of the original video. I only paused it here to add in commentary, but I didn't cut anything out. So that's the whole story for Gyro 1. Alright, this is gyroscope number 2, and it's a heading indicator. I have it set up here, and this time I will be calculating the drift in degrees per hour based on 5 degree, how long it takes to move 5 degrees to save time, because waiting for it to move more than that takes more time, and measuring in between marks is difficult, so it's easier to line it up to a mark and then see how long it takes to move a full 5 degrees. So this is the time of day that the pictures were taken, and I've got a calculator here. What I'm doing here is, this is my 5 degrees. This just converts the time, see, 13:01:24 becomes 13 hours, 1 minute, which is a 60th of an hour, and 24 seconds, which is a 3600th of an hour. So that's our start time. So now we let this play. Actually, there's our start time. That's a little more lined up there. So 13:04 and 35. Okay. I'll let this play, see how long it takes to go from 0 to 5 degrees. Now this gyro has quite a lot of drift, just due to imbalance from the mechanism inside of it, and its drift actually exceeds slightly the rotational rate of the Earth of 15 degrees an hour. So it's pointing south, and so it should be registering the other way, except its drift is faster than the Earth's rotation, so it's showing a positive drift. I'm going to weight that. Okay, right there. And that's probably about lined up. So it took us from 13:04:35 to 13:42:12 to move 5 degrees. So 13:42:12. Okay, we moved 7.9, almost 8 degrees in an hour, per hour. Now we'll let this play, and then it goes past, and then I'll rotate the whole thing around. In the video you'll see it. And I'll set it up, and there. Now we're pointing north. Now we should not be picking up the Earth's rotational effect. And you'll notice that it's drifting much faster because that's the drift the gyro has, but before it was being cancelled by the Earth's rotation. So now we are gonna have a start time of 13:51 minutes and 50 seconds. See how long it takes to move 5 degrees. See, it's moving much faster now that it's not being countered by the Earth's rotation. Okay, right about there. I guess that's close enough. Okay, so our end time is 14:04 and 06 seconds. Interesting, we moved 24.45 degrees per hour. Now, what we need to do is subtract the one from the other to get the difference. And that is the effect that the Earth's rotation had on the gyro. It caused a difference of 16.48 degrees per hour, which is not exactly 15, but it's an old worn-out gyro. So let's do the next one, because this test went on for some more time. Let's get past there, and then I rotate it around. Because remember, each second here counting is worth a whole minute. Okay, so now it's pointing south again. See, now it's moving much slower because the Earth's rotation is countering the drift of the gyro, but I'm waiting till that point is lined right up there. And now I am going to take our starting time of 14 hours, 25 minutes, and 11 seconds. See how long it takes to move 5 degrees. Yeah, you can see I've got some LED lights here. There's 4 of them. You can see 3 of them in the reflection. They kind of flicker a little bit, and they're causing this funny pattern. Okay, we're almost to 5 degrees. We're is that about close? Okay, I'm gonna call it good enough. The numbers are all here. You can redo these experiments here if you want. So, alright, so our ending time is 14:54, so 14 hours, 54 minutes, and 06 seconds. Okay. And we got 10.37 degrees per hour that way, so it's gone up. See, it was about 8. So it's going a little bit higher than it was earlier. But now let's go ahead and do the second part of this. Okay, now we get it flipped around. Now we're pointing north again, and right about there. So our starting time is 15 hours, 15 o'clock, 05 minutes, and 55 seconds. See, it's moving right along now that it's pointing north and the Earth's rotation is not affecting it. It's not countering its internal drift. And right about, I don't know, is that about right? Okay. So our stopping time of 15 hours, 15 o'clock, 18 minutes, and look at that, 55 seconds. 23.08 degrees. So now let's take the difference of these two numbers, the one pointing north and the one pointing south, and it's 12.7 degrees. So that's kind of under 15 degrees an hour, but like I said, it's an old compass. But let's average out this slightly high value we got before and this slightly low value we got today, or this time. So, as you know, you can take an average by adding the two together and dividing by 2. Look at that, an average of 14.6 degrees per hour of drift. And that's the drift difference based on the Earth's rotation. So that's about it. This just went on for a little while longer, and that was the end of the test. Yep, that was it. So there you have it. Gyro number 2 gave 14.6 degrees per hour of drift, averaged from its multiple readings. And that's the drift of difference based on whether it's pointing north or pointing south. That is to say, lined up to the North Star, the rotational axis of the Earth, or at right angles to it. Okay, this is gyro number 3. It's a gyro compass, a heading indicator, and I have it set up here, and I'm going to, on this one, we're going to run it pointing north for a little over 15 degrees and time that, and then we're going to run it pointing south for a little over 15 degrees and time that. So this is our starting position. We're pointing north, so we're just measuring the internal drift in the gyroscope, and this one is drifting in the same direction that the Earth would cause it to appear to rotate. And so we'll see how that works out. You can see my starting frame, the mark is not quite lined up, so when I get this white bar over to here, the 15-degree mark, I'm going to try to line it up with the mark behind it still showing out a little bit. So that's why it's going to be a little bit past over here, because it's a little bit past here. So I have our calculator going. Our starting time is 17:00:22, and let's go. So you can see this one's got quite a lot of drift. It's pointing north, so this is just its own drift. Remember, this is 60x speed, so this is 12 minutes, 13-14 minutes, not seconds. It's playing at 1 minute per second, so. Okay, we're almost there. Okay, comes behind, and it starts to peak out. So remember how this was starting to peak out? I got this one peaking out about the same. So now our ending time is 17:32:11. So we moved 15 degrees, 5, 10, 15 degrees in that much time, and it was 28.25 degrees per hour is the drift without the influence of the Earth's rotation. Okay, now we're going to go ahead and play a little bit more. You'll see I come in and turn it around. I didn't really turn it that fast, but it's playing at 60x, so okay. Alright, so there is our starting time. So we got the mark right on the line right on the mark that time. So our starting time is going to be 17 hours, 17 o'clock, 42 minutes, and like 41 seconds or so. 17, 42, 41. Okay, good. Now let's see how long it takes. See, now it's pointing south, so it's moving with its own drift plus the Earth's rotation drift. So it's really moving along fast now. 10 degrees. We're getting there, and I'm going to call that about right. So 18:03:32. So we've got 18 o'clock, 3 minutes, and 32 seconds past. Wow, so with its drift plus the Earth's drift, Earth rotation drift in the same direction, it was turning at 43 degrees per hour. So now to get the, remember the first one we did pointing north, which would not be measuring the Earth's rotation, because I'm in the northern hemisphere and it's tilted up, so the gyroscope is pointing straight at the North Star. So this one was without the effect of the Earth's rotation, and this one was with the effect of the Earth's rotation. So let's get the difference between these. Wow, 14.87, that's basically 14 point, that is very close to 15 degrees an hour. So gyroscope number 3 confirms that the Earth is rotating at somewhere close to 15 degrees an hour.